So in this video, I'm going to look at the exam questions that come at the end of 25.2. I'm not going to go through all of them because you've already got the mark schemes, just one or two that people tend to find difficult. So I'm going to look at question number 3, the number of sigma bonds in a benzene molecule. So I've drawn out benzene, and rather than drawing it with the kind of delocalized model, I've drawn it out with alternating double and single bonds, just so it's easier to count my sigma bonds. So you have got 1, 2, 3, 4, 5, 6 carbon hydrogen sigma bonds. You have also got 1, 2, 3, 4, 5, 6 carbon-carbon sigma bonds. Remember, even where you've got a pi bond, okay, you've also got a sigma bond. So I've got sigma bonds between all of the carbons and between the carbons and the hydrogens. That gives me 12 in total. That means the answer is D. The next couple of questions all refer to the kind of the Kekulé localized model and the experimental evidence. I'm just going to highlight one or two things on the mark schemes from just one of the questions. So when you're talking about the orbital overlap, you have to specify p orbitals. You can't just say the orbitals overlap. You have to specify p. And when those p orbitals overlap, they are forming pi bonds. So they're the key. The p and the pi are key in order to get the marks. The other thing you need to say is that this is above and below the plane. So you've got electron density, or these pi bonds, above and below the plane of the ring. Okay? When you're talking about your difference, you're talking about the electrons being localized in Kekulé's model, and you're talking about the electrons being delocalized in the other model. You should use diagrams, and they really help with your answer. In case you forget to say something in your written response, a diagram can help pick up the mark. But if you look again, they're very particular about what they will and won't accept. So you have to say p orbital, just like I highlighted above, to get that first mark. You shouldn't be talking about, or what they don't care about, the s orbital overlap in your carbon-hydrogen bonds. That's not required. Your label diagrams, as long as you're labeling it properly, see pi bond, pi electrons, again, you're specifying. And again, this diagram is showing the electron density above and below the plane of the ring. So if you'd forgot to mention it in your written response, you would get the mark for showing it here in your diagram. Other thing I was going to say is, if you look at the examiner's comments on this question, it says that Kansas found the question really difficult. I don't really get that. It's very clear from the mark schemes what you need to be including in your answer. It's a standard question that comes up all the time. Make sure you know exactly how to answer it. It's not, a random question that came out of the blue. You should be prepared for these types of questions. Even though they're conceptually a little bit tricky, they have a very set answer format, and you need to make sure that you know it. They're not marks that you want to lose when it's a question that gets asked so often. After the kind of structured questions, it moves on to the reaction questions. Okay, so for this one here, suggest the reagent that's required. So you can see you're adding a carbon, double bonded to an oxygen, bonded to a CH3. That's what you're adding to the benzene ring. Okay, but before this carbon was bonded to the benzene ring, it must have been bonded to something else. It didn't have 3 bonds until benzene came along. It always had 4. You want to make this carbon a really good electrophile for the benzene to be able to attack. If I want to make it a really good electrophile, I'm going to attach it to something more electronegative, something like a chlorine. And they give you that option here as C, CH3, CO, Cl. Your answer is going to be C. The next question is about the nitration of benzene. In this case, it's benzoic acid, but it doesn't affect how you do the mechanism. It's exactly the same as the one that we did in our notes. What you do need to be mindful of is the position. Because you have the carboxylic acid group there, you do need to make sure that you're putting the nitro group 2 carbons away. And when you're drawing your intermediate, that's the only step I'm just going to show. When I'm drawing out my intermediate, and I've first attached my NO2 group, I need to make sure that my semicircle is pointing towards that NO2 group, okay? But other than that, it's exactly the same. You're going to do out your 3 steps. It even prompts you here to show step 1 by asking how H2SO4 behaves as a catalyst. And to answer that part of the question, you just write the equation from step 1 like we had already done. This question here it's obviously something that we didn't go through in the notes, but they give you all the information that you need. Yes, it's an unfamiliar kind of reaction. But if you know electrophilic substitution, you know the mechanism for it, it's going to be the same as what we've done before. So I know from all of the other mechanisms that we've done that benzene is my nucleophile. Here I've clearly got an electrophile, I've got a delta positive sulfur. So what's going to happen is the benzene is going to attack that sulfur. And if you're in any doubt, you just look at the product. You can see that the benzene is now attached to the sulfur. So you're asked to include curly arrows. I know I'm going to be starting my curly arrow at the nucleophile because I always do. It's going to start there in those pi electrons. It's going to come down here. I'm going to be attacking the sulfur because I can see I'm forming a new carbon-sulfur bond. I can also see in my product, because sulfur already has 6 bonds, which is the maximum it can have. So if I'm going to form a new bond, one of those bonds must break. And if you're in any doubt, just look at the product. You can see that you're missing one of those double bonds. So I'm going to start my arrow on the double bond and I'm going to end it on the oxygen. Okay, so it should start from the middle of the double bond and end on the oxygen. And now I need to draw my intermediate. And again, this intermediate is going to be quite similar to what we've seen already. So I'm going to draw out my benzene ring. I'm going to put in my CH3 up here. Now I'm going to be putting in my sulfur, which is bonded to, okay, so just as it looks below. And I'm going to draw my positively charged intermediate, okay? And when I do that, I'm going to be drawing the following, okay? The positive charge, that semicircle, has to point towards my new substituent. And I can see here I'm removing a hydrogen. So I need to show that hydrogen on the same carbon as the sulfur and start my arrow on that bond and bring those electrons back into the ring. That will reform my ring, which is what I've got in my product. So even though it's a different electrophile, not one that we've seen before, they do give you all the information that you need, and they're just asking you to apply knowledge that you should know in an unfamiliar situation. The last question here is a 6 marker. It says, and it's on electrophiles. It says many organic reactions use electrophiles. Explain the role of an electrophile in organic chemistry. So if you want to give examples of something reacting with an electrophile, you want to have a nucleophile. Okay, a nucleophile will react with an electrophile. And there's only 2 functional groups that we've studied in detail that act as nucleophiles. In chapter 13, we looked at alkenes. They are nucleophiles. And now in chapter 25, we're looking at benzene, which also acts as a nucleophile. So they're the 2 functional groups that we've studied that are nucleophiles and hence react with electrophiles. It also fits what they've asked for in the question, an aliphatic compound. So an aliphatic compound is anything that does not contain a benzene ring. So I just got a normal alkene that will not contain a benzene ring. That will be my aliphatic compound. An aromatic compound is something that does contain a benzene ring. So if I just use benzene itself, then it's my aromatic compound. So when I'm doing out this answer, what I'm going to do is I'm going to pick an alkene. I'm going to make it nice and easy for myself as well. I'm going to make it a symmetrical alkene, so I don't have to worry about major or minor products. And I'm going to write a mechanism for the reaction of alkene with an electrophile. And I can pick any electrophile. I'm just going to pick bromine, because then I'm going to do the same for both. I'm going to have my bromine, delta positive, delta negative. I'm going to draw out my electrophilic addition mechanism. So rather than writing this in words, I'm just going to do my mechanism instead because I know it really well. I have bromine there, attacks, and I end up with, and I would label that this is an example of electrophilic addition. That's the reaction type. And then underneath, I would do the same thing for benzene. I would take my benzene, I would react it with an electrophile. I'm going to use bromine again. I remember that when I react benzene with bromine, because benzene is less reactive, I do so in the presence of a halogen carrier catalyst. I'm just going to put my catalyst there. And I'm going to write my final product first. And then I'm going to show out my mechanism. You wouldn't need to show the entire mechanism with the step 1, the step 2, and the step 3. The step 2, where the benzene actually reacts, that will be the important part. So I'm going to show it reacting with a bromine with a positive charge. It reacts. I end up with my bromine. I lose my hydrogen. I regenerate my ring structure. kick off the H+, which will then go and regenerate my catalyst. And this is an example of electrophilic substitution. And the other thing I would add to this answer for 6 marks is I would just add the definition of an electrophile. I'd have that someplace. I would just say that an electrophile is an electron pair acceptor. Electrophile is an electron pair acceptor. So I give a definition, and then I draw out 2 mechanisms. And I wouldn't use words. I would just use my curly arrows and let that do the explaining for me, because it's far easier than trying to write it all out in words. So if we scroll down and have a look at the mark scheme for what they wanted in that question, lots of explanation of role of electrophiles in organic chemistry. So here they've used a similar reaction to I did, and they reacted with bromine. They've used displayed formula, I use skeletal, sorry, they used displayed, I use skeletal, it wasn't specified, so you can do whichever one you want. So, and then they used nitro, from the nitric acid. Again, they didn't show how that electrophile was generated, so they didn't show the step 1 or the step 3. They just showed the step 2, the reaction with the benzene. So there's your 2 reaction mechanism. And then they give some descriptions here, but this is not inclusive. You don't have to include all of this to get the marks. Electrons, electron pair acceptor. So I've done that. Types and names of the mechanisms, I've done that. Equations for generation of electrophile and regeneration of catalyst, so I didn't include that, but it's not inclusive. Accurately positioned and directed curly arrows and charges and dipoles included, so I've done that. Explanation of major and minor product from electrophilic addition, I've avoided the need to do that because I've chosen a symmetrical alkene, just like they have done in the mechanism. If you did choose an unsymmetrical alkene, though, you wouldn't have to include this information. As I said, it's not inclusive. So the examiner says that good answers were well organised with clear mechanisms and precisely positioned curly arrows, and most candidates also included a clear definition of an electrophile, and drew out the mechanisms. So your common errors and omissions were the direction of the curly arrow from the aromatic ring to the electrophile. So the aromatic mechanism was the one that was causing the problems. Some lacked detail and didn't give any kind of supporting words like the names or the definition of electrophile. And then lower ability candidates just got it wrong, had nucleophilic addition in there instead. A few candidates answered in prose, so they just wrote the whole thing out in words rather than including equations or diagrams. Candidates are advised that mechanism must always be communicated in the usual diagrammatic way, so don't write out the answer, use your mechanism. And there is an answer that's scored all 6 marks, and you can see very little writing, definition of the electrophile, but other than that, just the mechanisms and the names of the reaction type. Okay, so that's how you should approach those type of questions.